So in chapter 2, we introduce atoms and elements. So here's an interesting question. You don't have to answer it out loud, but just think about it for a minute. If you cut a piece of graphite from the tip of your pencil into smaller and smaller pieces, you took a piece and you cut it in half, and you took one of those pieces and you cut it in half, and you kept going, how far could you go? Could you keep dividing it forever? This is something that ancient philosophers thought about. Well, turns out that eventually you would end up with individual carbon atoms. Now, you can't actually do that with a knife, of course, but, thought experiment. You end up with individual carbon atoms. The carbon atoms cannot be cut in half. The word atom comes from the Greek word atomos, meaning indivisible. So this is like the essential smallest particle that matter is made out of. So atoms compose all ordinary matter, and if we want to understand matter, which is what chemistry is all into, then we need to understand what atoms are. So back in 1827, Robert Brown looked through a microscope at some water-suspended particles that had come from pollen grains. This really fine, dusty stuff, and it was suspended in water, and he's looking at it through a microscope. Now, here we have a date and a name. I'm not going to test you on the history of chemistry. I think it's interesting. It'll come up, in lecture, but you don't have to worry about when did Robert Brown look through a microscope. That's silly, okay? So he looked through the microscope, and he saw these little pollen grain particles, and they seemed to be moving. And of course, being a curious scientist, he's like, why are they moving? So I have a very short little video here that shows us what he was seeing. So you see the little particles, and they're jittering, right? The slide wasn't moving. He wasn't bumping the table. It looks like they're alive, right? Yeah, that is a short video. And I don't want to listen to the next one. So, big question was, what's causing the motion? Well, he initially thought, seems reasonable, the particles were alive. But he finally concluded that the source of that motion did not come from the particles themselves, but from something else. This was called Brownian Motion, after Brown, who first observed it. So fast forward to 1905, Albert Einstein came up with a theory that explained this Brownian motion. And the explanation is that those particles that we can see are jiggling around because smaller particles, water molecules that we can't see in the microscope, are hitting them. It's a little bit like a beach ball at a graduation or a football game or something, where they get the beach ball up in the crowd and people just keep hitting it, it just kind of goes all over the place, right? So the beach ball is the particle that you can see, and the people hitting it is the individual water molecules. The water molecules are moving around because of thermal energy. And so they cause the dust particles and the pollen particles to bounce around like that. So this inferred the existence of atoms. Now, people had, described atoms before, but nobody really had any evidence of atoms, and so this was kind of a big deal. So Einstein's work and the work of others removed any doubt about the particulate nature of matter. So it ended the debate of, can you divide it infinitely, or does it end up at a smallest particle? Now with the technology that we have, we can actually get images of individual atoms, not with a light microscope, but with an electronic microscope. So this came about in the 1980s. A couple of guys at IBM in Switzerland developed a scanning tunneling microscope. And the way this works is there's a computer that moves this probe. At the end of the probe is a very tiny tip, and the instrument passes a current from this tip through a small gap of air and into the piece of matter being observed. So what the computer does is it moves this tip around in a way that keeps that current constant. The current flowing depends on the distance that the tip is from the surface. So the computer is able to move this around and adjust it up and down so that it keeps a fixed distance from the atoms on the surface. Now the atoms are like, marbles sitting here, and so the tip goes up and down as it moves across. And that can get translated through the computer into digital images. And so here's an example of a scanning tunneling microscopic picture of atoms. These are atoms that have been moved around to spell out the Japanese word for atom in kanji characters. So these are red iron atoms on a copper surface, which is the blue. And you can see they're not perfect spheres, they're kind of distorted, and that's an artifact of the instrument. So I also have a couple of cool little movies that give a better explanation of STM than I'm able to do because, nice pictures. Can you press escape? Discard. I just want to watch the movie.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
And here's another one scientists like to have. Oh wait, that's not the one I want. Never mind. Okay. Before we watch the next one, does anybody have any questions about what that guy was describing? So, can you imagine how small the things are that they can build? They can build something where a wire is 1 atom wide. And IBM is, interested in making very, very small circuit boards and other very tiny things. These are things that can't even be seen with the highest powered visual microscope, but they're able to move individual atoms. And so you can make some very fancy technology, or you can also use this to make the world's smallest movie. So it's basically stop motion animation with atoms. So there's another video that, see how the movie was made. I'm not going to play that one in class, it's a little bit longer, but it is available on our YouTube playlist. Any questions? So you can't make a movie any smaller than that. The individual pixels are individual atoms. It's kind of crazy. Give you another idea of how small those images are. So you've heard of the Library of Congress, huge library in Washington, D.C. 35 million books. And if you lined up the length of the shelving, 840 miles of books on a shelf. So if you took all the words in all of those books and wrote them this size with the little, like the kanji characters, if all the letters were that size, all those words would fit in an area of 5 square millimeters. 5 millimeters on the side. That's half a centimeter. If that doesn't boggle your mind, I don't know what would. So, atoms are incredibly small, mind-bogglingly small. So in spite of their small size, though, those are the key to connecting this macroscopic world that we can see and deal with to the microscopic and submicroscopic world. So the atom, again, is the smallest identifiable unit of an element. You take any given element and you cut it in pieces, and eventually you get down to an atom. There are lots of different elements, and we have them up here on the periodic table. We'll learn a lot more about the periodic table and why it has that shape. There's 91 of the elements occur naturally, and then there's over 20 synthetic elements. Those are not found in nature, those are man-made. And so those are listed up there, and people are working on making new elements, and this periodic table is actually a little bit out of date because the rest of these elements with the U names, UUT and UUP, those all have names now.